Hi, this is Tom, and in this video we are going to talk about independence and dependence and how they can be illustrated by using a weighted tree. So I have written down here the problem that we're going to work with. It says, a jar contains 2 red and 3 blue marbles. Draw a weighted tree to find the sample space of drawing 2 marbles. Well, here we go. So the first one now, there's actually 2 catches. We're going to draw 2 trees. In the first tree, marble is replaced. And this creates what's called, I'm just doing an arrow, independent events. Now, in an independent event, I should give us a definition, is one in which the probability of what has happened does not affect the probability of what will happen. I think this will become more clear as we start our example. So here we go. Imagine we have some marble here. Marbles always have those neat little wavy things inside of them. Sometimes they're different colors. Maybe you could make a better marble. Now, when we're going to keep track of it the same way we did earlier. So we have our first draw. And what can happen? Well, you could either draw a red marble or you could draw a blue marble. Now, the probability of a red, well, if we look up above here, there's 2 reds, there's 3 blues. So 2 plus 3, that's 5. And so the probability of a red is 2/5. And the probability of a blue, well, that's 3/5. So now, if you're actually playing this game, you would then put the marble back into the jar, mix the marbles, and then you would take your second draw. Now, let's say, now because you put the marble back in, what has happened will not affect or does not in any way determine what will happen. So when you go to draw, you can either draw a red marble or you can draw a blue marble. Or maybe you do a blue on the first one, but on the second one you can still only draw either red or blue. Now, because we put the marble back in, notice that the probability of a red one is still 2/5. And the probability of a blue one is still 3/5. Or if you first drew a blue, then on the second draw, the probability of a red is still 2/5, and the probability of a blue is 3/5. So let's write here's our outcomes here. So if I wanted the probability of a red, well, we just follow what we've done before and we multiply the probabilities, which are also called weights, the weights on each branch. So that was 2/5 times 2/5, which is a total of 4/25. The next outcome is probability of a red marble followed by a blue marble. Well, that's 2/5 times 3/5. And notice that on the second one, we first got a red, then we drew a blue. And on that first one, I should have done another color, was first drawing a red and then drawing another red. So if we finish this out, the probability of a red then a blue is 2 times 3, which is 6, and 5 times 5 is 25. All right, let's go to the next one. And the next one is down here, and that red's not a very good highlighter color. So let's go down, we draw blue, and then we draw a red. So we're on this green set of branches. So this becomes the probability of blue, followed by the probability of red. So we multiply the weight on each branch. Well, the first weight is 3/5, and the second weight is 2/5. So we multiply 2 times 3 to get 6, 5 times 5, and we get 25. And then let's run out our final branch along our tree. That would be first drawing a blue and then drawing a blue again. So if I do that, the probability of a blue, that's 3/5 times 3/5, or 9/25. There. So that is what happens on independent events. Notice that the probability of drawing a red or a blue stays the same each time. Now, let's move to our second example. So this time, we're going to do our second, what did we call it? Second tree. Our second tree is once a marble is drawn, oops, it is withheld. Wow, let's see what happens here. All right, well, the question works much the same way. Again, we have some marble, and it's got some beautiful veins of color that run through it here. They look like that. So, but the same idea follows, and that is that we have two draws. So on our first draw, I can draw either a red marble or I might draw a blue marble. Okay, now if I draw red, the probability of drawing a red, we'll put our weight is there's 2 reds out of 5 in the jar. And the probability of a blue is 3 out of 5. Now, this time, we're so excited that we got our marble that we keep it, and then we proceed to our second draw. So, again, when you reach in, you could either pull out a red marble, or you might pull out a blue marble. But let's keep going. Maybe you got a blue on the first one. On the second draw, you can still either pull a red or a blue. Now, but let's do this. When you first drew a red, let's imagine a little sample space down here. When you first started out, you had a red, and then 3 blues in the bag. So if you first draw a red, and then it's now withheld, when you go to reach in on your second draw, notice a couple things. One is the sample space is no longer 5, there's only 4 left. And there's only 1 red. So the probability of the red on the second draw becomes 1/4. Similarly, say you started out and you had red, blue, blue, blue. If you first drew a blue and then you went to draw another marble, well, again, now there's only 4 in the bag. And this time there's only 2 that are blue. And so on the second draw, you'd say it's 2/4. And if we continue this, if we first draw a blue, then there's only 4 left, but then there'd be 2 reds out of 4 total. Or if you first draw a blue, now there's 2 blues left and 4 total. And now let's calculate the probabilities of each. So the probability now of red is 2/5 times 1/4. That's 2 times 1, or 2. 5 times 4, that's 20. Now, you could reduce these fractions, but it makes the problem a little bit more difficult to see. So we're just going to leave them. Let's do the next one. The next one is the probability, the probability of red than a blue. Well, the probability of a red is 2/5. Notice I'm just taking the weights, and then probability of the blue is 2/4. So just for clarity, I'm on the second branch here and then here. Let's go down to our third branch. That is first a blue and then a red. So that looks like a 3/5 and a 2/4. All right, so we'd say the probability of a blue and then a red, well, that's going to be a 3/5 times a 2/4. And we have one more branch on our tree. Let's do that in our, I like this pink color. So that would be a blue and then a blue. So let's see. That would be the probability of blue, blue, and that is 3/5 times 2/4. And let's multiply these up. So 3 times 2, that's 6 over 20. This next one is 6 over 20. And above that is 4 out of 20. Now we should always make sure that if we add these together, we get 1. So let's do that. So if I take 2 20ths and I add to that 4 20ths plus 6 20ths plus, how many more? 6 20ths. Well, let me see here. That's going, I think I made a mistake. Oh, I did make a mistake. Oh, here's my mistake. Let's go fix that while I see it. Notice the mistake was right. Let me highlight it for you first. It was right here. Couldn't even use my own drawing very well. Notice down here we used, if I went way back here, that what we said was that there was originally, I'm sorry, is this one. If we first draw a red, then there's 3 blues in there. So it shouldn't be a 2, this right there, that should be a 3. So let's go fix it over here as well. And we need to fix our last bit of multiplication. So that would be a 6. And fix that one. That will be a 6 as well. There we go. So 2 plus 6 is 8, plus 6 more is 14, plus 6 more. And there it is, 20 out of 20. So we would say that the answer is really 1. Now, that is the difference. So let's go do something kind of interesting. Let's come up here, and I'm going to just cut these outcomes. And so let's do that. We're going to copy those, and let's bring them down here. And I'm going to put them, oh, I didn't want that line, but we'll put them about like that. Because here's what I want you to see. There we go. What I want us to see is, notice that even though here's the same outcome, this first column is dependent and the second one is independent, and notice that you actually get different values. Here's 2 20ths, but when they're independent, it was 4 25ths. Then for red blue, when they're dependent, it's 6 out of 20, but when they're independent, it's 6 out of 25. Those are actually different numbers. Again, for dependent blue-red, it was 6 out of 20, but for independent, it's 6 out of 25. And finally, our last one was 6 out of 20 for dependent blue-blue, but 9 out of 25 for independent blue-blue. And that's how independent and dependent events can even be illustrated using weighted trees. think you'll find that the nicer your tree, the easier it is to find the answers. Hope that helps, and thanks for watching.